Ever wondered how the magic of digital design unfolds? How do circuits come to life from mere lines of code? Well, the secret lies in the power of a language called Verilog HDL. It's the unsung hero behind the scenes of every electronic marvel you've ever admired. Verilog HDL is a hardware description language that's used extensively in industries and academia to model, design, and verify electronic systems. Imagine it as a magical blueprint that helps engineers and researchers breathe life into circuits, creating the digital world as we know it. From the smallest microchip to the largest supercomputer, Verilog HDL is the wizard of the digital realm, silently crafting the wonders of technology. It's like the master key to the kingdom of digital design, unlocking the potential of electronic systems and crafting the future of technology. So, are you ready to delve into the fascinating world of Verilog HDL? Dive in to unravel the mystery of Verilog HDL, the language that brings circuits to life. So, what exactly is Verilog HDL? Let's demystify this coding language. Verilog HDL, where HDL stands for Hardware Description Language, is a programming language that has revolutionized the way we design and document electronic systems. Its origins can be traced back to the late 80s, specifically to 1984, when it was developed by Gateway Design Automation. Since then, it has been an integral part of electronic design automation (EDA) industry, being used by engineers worldwide to create and analyze digital systems. Now, one might be curious, why Verilog? What makes it stand out in the crowd of numerous programming languages? Well, its strength lies in its versatility. Verilog has the unique ability to describe the behavior and structure of a digital system at multiple levels of abstraction, ranging from the system level to the gate level. This flexibility makes it an ideal tool for integrated circuit and system-on-chip design, including design specification, design verification, and synthesizing the design to physical hardware. But it's not just about designing chips. Its application extends to the realms of FPGA programming and ASIC design as well. FPGA, or Field Programmable Gate Array, is a type of integrated circuit that can be programmed in the field after manufacture. ASIC, or Application-Specific Integrated Circuit, on the other hand, is a type of chip that is designed for a particular use rather than for general-purpose use. So, Verilog is the key that unlocks the potential of these technologies. Now, I want you to imagine something. Imagine you have an idea, a concept for a digital system. Now, how do you bring it to life? How do you translate it into a physical entity? That's where Verilog steps in. It provides a platform, a language to express your ideas, to describe the behavior and structure of your system. It's like the blueprint for your digital architecture. Verilog HDL, in essence, is the bridge between your creative ideas and the actual hardware that brings them to life. Now that we know what Verilog HDL is, it's time to understand its structure. When we talk about the basic structure of Verilog HDL, we're essentially discussing how Verilog code is organized. And much like a well-constructed building, good Verilog code is built on a solid foundation: modules, ports, and the main body. First, let's talk about modules. In Verilog, a module can be thought of as a building block. It's a piece of code that does a specific task, and it can be used over and over again. Each module has a name, and you can think of this name as the label on the building block. When you're constructing your Verilog program, you'll be stacking these modules together to create your final product. Next up, we have ports. Ports are the interfaces between modules. They allow modules to communicate with each other, passing information back and forth. There are three types of ports in Verilog: input ports, output ports, and in-out ports. Input ports receive data from other modules. Output ports send data to other modules, and in-out ports can do both. Lastly, the main body. This is where the bulk of your code will go. It's where you'll define what your module does and how it interacts with other modules. It's the heart of your Verilog program, and understanding how to structure it effectively is crucial. Think of it this way. If Verilog was a play, the modules would be the characters, the ports would be the dialogue, and the main body would be the plot. And just like in a play, each element has a crucial role to play in the overall production. But remember, understanding the structure is just the starting point. The real magic happens when you start combining these elements in creative and innovative ways. That's when you'll truly start to see the power and versatility of Verilog HDL. A solid grasp of Verilog's structure is your first step towards mastering this versatile language. Ready to get your hands dirty with some coding? Let's write our first Verilog code. Picture a simple real-world scenario. A single light controlled by a single switch. In the world of digital systems, this is a basic 1-bit memory cell, also known as a flip-flop. Let's translate this scenario into Verilog code. Start with the keyword module, followed by the name of the module. Let's call our module flip-flop. After this, we list the inputs and outputs inside parentheses. For our scenario, we have one input, the switch, and one output, the light. So our code starts like this: module flip-flop, switch, light. Next, we declare the direction of our inputs and outputs using the keywords input and output. Our switch is an input and our light is an output, so we add input switch, output light. Now the fun part begins. We'll create the logic for our flip-flop. In essence, when the switch is flipped, the light changes state. If it's on, it turns off. If it's off, it turns on. This is the behavior we need to describe in our code. We use an always block to describe this behavior. Inside this block, we write posage switch, light equals sign tilde light. This line says that at the positive edge of the switch, that is, when the switch is flipped on, the light should change to the opposite of its current state. This is the core of our code. But before we finish, we need to end our module with the keyword end module. So the final line of our code is end module. So here's the complete code. Module flip-flop, switch light, input switch, output light, always posage switch, light, equals sign tilde light, end module. It's important to understand each line of this code as it forms the foundation for more complex digital systems. Congratulations, you've just written your first Verilog code. This is just the beginning of an exciting journey. As we wrap up, let's revisit the key points we've covered about Verilog HDL. The journey we've embarked upon today has introduced us to an interesting and complex world of digital design, all through the lens of the powerful language of Verilog HDL. We began by understanding what Verilog HDL actually is. It's a hardware description language, which is a type of language used to describe, model, and verify digital systems such as microprocessors and memory systems. Verilog HDL, in particular, is widely used in the design and verification of digital circuits at various levels of abstraction. Remember, it's not just a programming language, but a tool to describe the behavior and structure of digital systems. This distinction is crucial, as it sets Verilog HDL apart from other languages such as Python or Java. It's all about digital systems, from the simplest of logic gates to the most complex microprocessors. Next, we dove into the basic structure of Verilog HDL. We discussed how each Verilog program consists of a module, which is the smallest independent unit of the language. A module encapsulates the functionality of a digital systems component, and these modules can be instanced in other modules, creating a hierarchical design. We also talked about the different types of data in Verilog HDL, including nets and registers. Nets represent physical connections between hardware, while registers represent storage elements. We also highlighted the importance of always and initial blocks, which are procedural blocks in Verilog that allow us to describe the behavior of digital systems over time. Then, we took our first steps into writing a basic Verilog code. We used a simple AND gate as an example, starting with declaring a module, defining inputs and outputs, and finally, describing the behavior of the gate. This exercise gave us a first taste of how Verilog HDL can be used to design and simulate digital systems. In conclusion, Verilog HDL is more than just a language. It's a bridge to the world of digital design, a world that is increasingly becoming a part of our everyday lives. From the smartphones in our pockets to the self-driving cars of the future, digital systems are all around us. and Verilog HDL is one of the tools that make these systems possible. Learning Verilog HDL is not just about memorizing syntax or understanding logic. It's about developing a new way of thinking, a new way of problem solving. It involves understanding how a digital system works, how its components interact, and how to design and verify these systems. Verilog HDL is a powerful tool in digital design. With a little practice, you'll soon be designing your own digital systems. Until next time, keep coding and exploring the world of digital design.